So dear students, today we shall learn determination of composition of a metal complex. Composition of a metal complex. Now in this we have two important exercises. So actually for determining the composition we are having different methods. One is mole ratio method, or it is also called molar ratio method. Second one is solubility method. Thirdly, we have spectroscopic methods. In this we have Jobs method. Apostrophe this. His full name is Paul Job. And so this is Jobs method. Another one is slope method. So among these different methods we have in our syllabus, mole ratio method is there and we have Jobs method. So these are the very important stock questions. How we can find out the composition of a metal complex either by using the Jobs method or by using a mole ratio method. So just now we shall deal with these things one by one. So first of all we must know, that is in our lower classes we have learned how we can express the concentration of a solution. Generally for expressing concentration of a solution we have different methods. One is molarity, then we are using mole fraction. Mole fraction generally is represented by X letter. Then we will use capital letters. Mole fraction. I want this one. So here we are making use of this mole fraction. That is one of the method for expressing the concentration of solutions. So while determining the composition of a metal complex, whether we are using solutions or not. So here, for getting a metal complex, we need a metal atom or metal ion solution, and secondly we need ligand solution. So we are using the solutions, so definitely we must express their concentrations also. So here especially we are using this mole fraction. That is one of the methods for expressing the concentration of any solution. So now here, in the case of a solution means generally we have a solute and another one is a solvent that will give us a solution. Yes, we know it. That is it, because itself we have learned all these fundamentals. Now solute and solvent, it is giving rise to a solution. Now here let us take metal solution and another one is a ligand solution. Then we are getting a complex. So a metallic solution, metal and ligand solutions, when they are combined, then we are getting a mixture. Solution is also a mixture. So in this mixture we are having a metallic complex. Now how we have to find out its molecular formula? Generally the complex is represented by M, L, N. Here must be a subscript. So here number of ligands. N stands for number of ligands. And M is the metal atom or it is a metal ion. Okay. So depending upon the coordination number of this metal. Suppose if the coordination number of the metal is 4, coordination number if it is 4, then its formula will be ML4 you will write. Then it will have two structures. One is either it may have tetrahedral structure or it may have square planar structure. And suppose if the n value is 6, then so coordination number is 6, then the formula will become ML6. That is a octahedral complex. So in the case of octahedral complex, it is having ligands number is 6. They are a ligand generally. It is a Lewis base. What is a Lewis base? A chemical species that donates a pair of electrons to this metal and it is forming a coordinate covalent bond or a dative bond. So the number of dative bonds formed by a metal ion directly with the ligands, that constitutes the coordination number that we have already learned in the first chapter, isn't it? Now here, how we have to find out this composition, that is a formula, molecular formula of this metal complex. For that we are having two methods, that is Jobs method and mole ratio method. Now we are discussing about these things, that is mole fraction is the concentration method that is employed in the case of either Jobs method or the mole ratio method. How it is related. Now here let us consider the metal solution. It is having a concentration of M. So concentration of metal solution is Cm and concentration of ligand solution is same, is M. Now come to the flashback of your 10th class, that is in solutions chapter. We have learned that number of moles of solute is represented by M1, number of moles of solute is represented by M2. So here in this case, the mole fraction of solute, that is X1, is equal to, you will write, we have learned already, N1 by N1 plus N2. So number of moles of the solute by total number of moles in a solution. Like that we have learned. So how we can calculate the mole fraction? Mole fraction is calculated by the formula number of moles of that component by total number of moles in that given mixture or solution. So now here come to this metal ligand complex. Now in this case, we want mole fraction of the metal ion. So first I will write here mole fraction of metal ion solution and mole fraction of ligand solution. So we have to find out separately mole fractions of both the ligand as well as the metal. Now how we can find out? Here in this case we have written number of moles of the solute by total number of moles in the solution. Now in terms of concentration, how we can write? The concentration of the ligand is here. So I can write like this. That is the mole fraction of ligand, say it is XL is equal to, then I can write here CL by CL plus CL. Why I have written plus here? Because the total concentration in the solution, that is in the case of a complex, that is present in the denominator. And this is the CL, it is the concentration of the ligand solution. So now suppose if I want the mole fraction of the metal ion solution, say XM, then I can write here Cm by Cl plus Cl. So in denominator term it will change. Here we have selected only two components. Now Jobs method also it is applicable only for two component system, but we should not increase the number of solutes. If it is more than two, we are not using this method. So here only two components must be there. One component is a metal ion solution and another one will be a ligand solution. Okay. Now here there is one rule. What the rule says? The mole fractions of all the components, mole fractions of all the components present in a solution. Now, just now I have written in the beginning that is a solution is having only two components, one is a solute, another one is a solvent. Is it not? Now here we are taking only two components. So the mole fractions, of all the components, its sum, that is the sum of. So sum of mole fractions of all the components is equal to unity 1. So here we have metal ion solution whose mole fraction is, say, it is X1, and mole fraction of the ligand solution, let us consider it is X2. So X1 plus X2 will be equal to 1. So this is the rule that is the same. So generally, even if the more number of components are present in a mixture, then if we add, sum means addition. So the sum of mole fractions of all the components present in that mixture, if it is added, then we will get this, that is equal to 1. So now, here I can write now plus. That is mole fraction of a metal ion solution whose mole fraction plus mole fraction of the ligand solution, that must be equal to 1 as per this rule. Now let us imagine mole fraction of the ligand solution, assume it as X. Then we can find out this one, that is mole fraction of metal ion solution is equal to, X will go to that side. So it will become 1 minus X. Okay? 1 minus X. Mole fraction of the metal ion solution will become equal to 1 minus X. In the beginning I have written in terms of concentrations. I told you that is mole fraction of the ligand is equal to Cl by Cl plus Cl. That is one equation. Now here we want to calculate its composition, what that composition includes. Now metal, it is combining with the n number of ligands, then we are getting n, L, N. This is the complex we are getting. Now we have to find out this n. How we can calculate that n? N is equal to, that is the number of ligands present in the coordination sphere. So n is equal to mole fraction of ligand by mole fraction of metal ion solution. So already we have assumed this mole fraction of ligand as X. So that is equal to X by mole fraction of the metal ion solution is, it is 1 minus X. So we get like this. So this is the equation 3. So for determining the composition of a metal complex, we are using this formula, that is number of ligands, how we can find out. That is by this formula, that is X by 1 minus X. What this X stands for? It is the mole fraction of the ligand solution. And what about this 1 minus X? That is nothing but the mole fraction of the metal solution. Okay? Now I am going to the actual procedure. How we can find out this n number by Jobs method as well as the mole ratio method. So here I will write mole ratio method. This is another question. Mole ratio method, and here we have Jobs method. Now come to this jobs method. In the jobs method, first prepare metal ion solution and ligand solution separate. In the jobs method, the concentration of this square bracket, you must read it as concentration. So concentration of metal ion solution, it is equal to the concentration of ligand solution. So here in the case of Jobs method, we are using two solutions. When these two solutions are mixed, then we will get a complex. Isn't it? So metal ion solution, it is mixed with the ligand solution. So by this we are getting a complex and we are determining the composition of this complex itself. So this complex is having the general formula MLN. This N we have to find out by using these two methods. Now, so first important aspect in Jobs method is the concentration of metal ion solution that must be equal to the concentration of ligand solution. Now I am coming to this mole ratio. Here in this case, metal ion solution, the concentration of metal ion solution, it is not equal to the concentration of the ligand solution. That is the main difference. Okay. So now I am proceeding with this one. So we have prepared two solutions, standard solutions by using the standard flask. So metal ion solution we have prepared and ligand solution we have prepared. Now we are doing secondly, let us take 10 test tubes and mix these solutions in such a manner that, say for example, the volume of metal ion solution, say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, from 0 to 9. Now it is a total 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now volume of ligand solution, whose volume will be here is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now total volume. What this constitutes? It is the complex. The volume of the complex solution will be same. That is 10, 10, 10, 9. So we are preparing 10 ml of a solution. Concentrations are same, but we are mixing in 10 different proportions. Now here in the first test tube we have 0 volume of metal solution. We have not at all taken metal solution. Just we have taken 10 ml of the ligand solution. Now second test tube is having 1 ml of metal ion solution and 9 ml of ligand solution. Like that we have prepared 10 different sample solutions. Are you following please? So up to this extent read out please. Okay? Now. So we have prepared 10 solutions. What for we have prepared this one? First, after preparing this one, we must find out lambda maximum. This is the other important aspect. This point is common both in the Jobs method as well as in the mole ratio method. Now come to this lambda maximum. You just understand what is its meaning. Now we know that light, it is having wavelengths. Lambda, wavelength is represented by lambda. So generally, we may use either UV light, ultraviolet, or we can use visible light also. Visible. Ultraviolet light, it is having 200 to 400 nanometers. And this one is having 400 to 800 nanometers. Now, we are taking, say, From 400 we are proceeding. 400. We are taking here only visible light. Now, lambda maximum means. Now we are taking a solution of any compound. Now incident the light on that particular solution. Then every solution is having the ability or capacity to absorb that light energy. A quantum of light is called as a photon, so it will absorb the light energy. So how much amount of light energy has absorbed, that is named as absorbance. So here, for having values of this either absorbance or after absorbing a part of the light energy, it may transmit some of the light also. That comes under transmittance. Already you have learned in your third semester spectroscopy in detail. So we can have, when I say light energy means, it will have a particular wavelength, it will have absorbance value, it will have transmittance also. So now here, in the case of for measuring either this absorbance or transmittance, we are using a device that is called as a spectrophotometer. So we are using a spectrophotometer. So in this spectrophotometer, for keeping this solution, we have a small complex structure that is called as a cuvette. So now in this spectrometer, by using this spectrometer, we are determining how much amount of light energy is being absorbed by a complex solution. Now we have prepared here 10 different solutions of the same metal and organic complex. Now here, let us select any one sample. Now for our convenience, I have taken here 5 plus 5, that is a 10. That means volume of metal ion solution in that test tube is 5 ml, volume of ligand solution is also 5 ml, and we have taken this sample solution. That solution is added into the cuvette, kept it in the spectrophotometer. Now, first allow 800 nanometer wavelength possessing light to fall on this particular solution, that is 10. Okay. Now find out what is its absorbance. Say for example, we got say some value 441 like that. That is the answer. Next, the wavelength of light must be 799 nanometers. Then what is the absorbance? So here, this reading, we can get it directly from this spectrophotometer. Okay, so like that here, first we have started with the light having the wavelength 800 nanometers, then we have proceed with 799, then 798. Like that, we have to move up to 400 nanometers. So, for all these specific wavelengths, what is the absorbance of that particular solution? We have not changed the solution yet. Solution is the same, but we are changing the wavelengths. Now we are measuring its absorbance. Now plot the graph. Now here, generally in the case of the graph, x-axis, y-axis is 0. Absorbance is taken on the y-axis and wavelength is taken on the x-axis. It is increasing like this. Absorbance values are increasing like this. Now we get this curve like this. This is the graph we are getting by plotting a graph between absorbance and wavelength. Now, by extending this curve like this, then it will intersect at a particular point. Now this one, that is the here actually this point, that is the peak that we have got here in the graph. This represents a maximum absorbance at a particular lambda value. So what is lambda maximum? Lambda maximum means the absorbance of a solution, the absorbance of light energy, by a solution at a particular wavelength. It must be maximum. That is the maximum value we got. So that is called as the lambda maximum. That means the absorbance value will be highest. So that is the maximum amount of light energy that is absorbed by that particular solution at a particular wavelength. Generally, every complex metal complex solution, it is having a constant lambda maximum. Say for example, let us cite MnSO4. Now here manganese metal whose lambda max we have abbreviation. Now its value is 525 nanometers. Now if you take iron complex, FeSC. Now here it is 490 nanometers. Now if you take potassium dichromate, K2Cr2O7. Now here chromium metal, it is exhibiting lambda maximum at 440 nanometers. So here in the third point, what we did here is, first we have to find out at what wavelength that particular solution can have maximum absorbance. That is called as the lambda maximum. We have to find out this lambda maximum. For finding out this lambda maximum, we are using a spectrophotometer, and with the help of spectrophotometer, by changing the wavelengths from 800 nanometers to 400 nanometers, then we have to plot a graph between absorbance and versus the wavelength. Then we get this graph. From this graph, we have to find out this peak. This peak is called as this is lambda max. So it is a fixed value. Now, after determining the lambda maximum, what we are doing in the next case? Foot. Here we have prepared 10 sample solutions. Isn't it? Now in the last aspect, what we are doing is take the first test tube, which is having a solution that is 0 plus 10. That means we are having only pure ligand solution. There is no metal. Metal ion solution is not there. So this sample is kept in the spectrophotometer cuvette. Then in the spectrophotometer we have to adjust its lambda maximum. I told, say for example, if it is 525 nanometers, we got as the lambda maximum from this value. Keep that wavelength only. Then use this first sample and determine its absorbance. Next, take out the solution. Next, take the second sample solution. Keep it in the cuvette. Now it is exposed to 525 nanometer wavelength light. Then what is the absorbance? That is like that we are getting 10 absorbance values. So in the last aspect, what we are doing here is we are fixing the lambda maximum, and these sample solutions are allowed to expose for that particular wavelength, and we are determining from the spectrophotometer their respective absorbances. Now we have to plot a graph between, so this is 0 x-axis and this is y. Here on the y-axis we are taking absorbance itself. Now here on the x-axis we are taking mole fraction of ligand. So mole fraction of ligand solution we are taking here. Now we get a graph like this. Same kind of graph. Now extend it like this. Then it will meet at a point. Now this point of intersection, from there we have to draw a straight line, perpendicular line to the x-axis. That is, perpendicular means must be 90 degrees. So a perpendicular line is drawn towards the x-axis, then it will meet at a fixed point. Now this will give us the mole fraction of the ligand. So here we don't need A value, absorbance value we don't need, we want this X. Already we have learned that N. Number of ligands, how we can find out this one? N is equal to X by 1 minus X. That is mole fraction of the ligand solution by mole fraction of the metal ion solution. So now we got from this graph X value. Then 1 minus X, right, the same thing. Then you will find N value. Suppose if the N value is 4, then metal will have, the composition will be ML4. If it is a 6 X value, then the complex is having ML6. Like that we will find out the composition of a metal complex. Okay, so this is a Jobs method. Now I am coming to the mole ratio method. So in the case of mole ratio method, just slight changes are there. In the first aspect itself, we have prepared metal ion solution and ligand solution whose concentrations are same in the case of Jobs method. But in the case of mole ratio method, we have to prepare different concentrations. That means the concentration of metal ion solution must be different from the concentration of ligand solution. So, say for example, metal ion solution is 0.1 m. Whatever it may be, 0.01 or 0.0, but it must be constant. Say, it must be maintained constant. And ligand solution, it is having different concentrations. So that is the first aspect. Concentration of metal ion solution is different from the concentration of the ligand solution. That is the first one. Now come to the second part. Here also we are taking 10 sample solutions. Now consider volume of metal ion solution. So here, now we are taking say 5 ml, 5 ml, 5 ml like that. And whose concentration is, say I have prepared 0.01 m. So all 10 solutions must have 0.01 m concentration. Now come to the next one, that is ligand solution, whose volume? Ligand solution. Now we have to prepare different concentrations. That means, say for example, one is 0.01, 0.02, 0.03, like that. Different concentrations we are taking. Now, 0.01. Let us take a 5 example. 0.02. So here, this is the first test solution sample, second, third, fourth, fifth, sixth, seventh, up to 10. Like that, only 5 ml, but here the concentration is only 0.0. In the next solution, 5 ml of ligand solution, but whose concentration is 0.01. Next in the second one, 0.02. Next, 0.03. Like that, the volume is the same, but its concentration is different. So total volume will be 10 ml only here also. So that is the main difference. So the concentration of ligand solution is different from the concentration of the metal ion solution. Like that, we have prepared 10 sample solutions. Okay. Now come to the lambda maximum. It is the same here also. In the mole ratio method also, we have to find out from graph, that is absorbance, and here is x 0 wave lambda, that is from 800 nanometers. What is absorbance? Then for 799, then up to 400 wave. What is absorbance? We have to find out. Then if this graph like this, now this maximum, this is a maximum absorbance at that particular wave. So I have given 3 examples. If it is a magnesium sulfate solution, then it will have 525 nanometers. If it is a iron complex, then it is having 490 nanometers. If it is a potassium dichromate chromium, it is exhibiting the lambda maximum at 440 nanometers. So like that, we are finding the lambda maximum in the case of mole ratio method also, that is one and the same. So in your notes also I have written here, this lambda maximum determination is the same as in the Jobs method. So that sentence you should not write in the examination, right? Because you have to write that information. Okay. Now last part, fourth part. What is the difference here? It is right. Now here we have taken, after finding out the lambda maximum, these 10 solutions, they are subjected for the interaction with a particular wave, lambda maximum light, and we will find out the absorbance. So here the graph is slightly different. So this is y-axis, 0, and this is x-axis. Here we are taking concentration of ligand by concentration of metal ion solution. So here this is a mole fraction of ligand solution by mole fraction of metal ion solution, that is nothing but N. So here in the form of ligand concentration by metal ion concentration, we are given here. Now the graph obtained is also different. So from the origin, a linear means a straight line. Here, so here, say first, second, third, fourth, fifth, then abruptly it will break at one point, and the graph, it will move down in the form of a slope. So here we get different points. Now this point of intersection, this view, from there we have to draw a perpendicular line to the x-axis. Then here we are getting this ratio, that is nothing but direct value, that is n. So if we know the n, we can easily write what is the molecular formula of that particular medium. Like that we are determining the composition of a metal complex. Okay, is it clear, please? So Jobs method and mole ratio method. So in the second unit, this is the second chapter. In this we are left with one more question, that is what is the stability constant and what are the factors affecting it.